All right, good morning and happy Tuesday. I'm planning on doing the daily challenge for LeetCode. So I'm going to record myself and share my screen here and see what LeetCode has in store for me here. So let's see. I'll do this in C++, it should be fine. All right, so basically we want to look at the longest consecutive sequence of an unordered array of integers. We have to do it in linear time. So obviously sorting is much more simple. We can't perform counting sort in O of n time. Oops, because the values x of the input array A are from -1 billion to +1 billion. It's just too many buckets. But here's the deal, right? Here's the deal. Oops. Sorting is simple. And it's a good start. So let's just do that. I just naive algorithm. Sort the input and O of n times log n time. Then reduce the asymptotic bounds there, right? For a linear solution, which is our end goal. Okay, so anyhow, let's just do this 616 hour minutes for the implementation in C++. Okay, so this is just going to be the naive sorting algorithm. Sort A, and then we'll do a run and the best run. Run is always of size 1. Best is what we'll return. Reach value x of the input array A. Keep track of last. No, let's do this for each index starting from I is 1 to the cardinality of A. So if a sub I minus 1 plus 1 is equal to a sub I, then it's a consecutive value. So best equals max best plus let's run. Otherwise, oops, run equals 1. Okay, so that should be the naive solution, running the best run basically. Okay, that's cool. Run these examples, those are good. 618, okay, so it's about 2 minutes, so which results in the wrong answer. A note to self, this is okay. Failure is an integral part of success. Winners choose to fail forward. The obstacle is the way. Okay, so anyhow, this looks like a corner case in that I'm saying the run is default to 1, but here I didn't look at the constraints in that the cardinality of the array, input array A could be 0. So, okay, let's do this. That's my first attempt. Second attempt for the bug fix should be pretty quick, I think. I just set the initial values to 0, and then it's 1 here. Okay, so actually, let's do this. If a dot empty returns 0, and then we can just keep these values the same, right? Just handle that corner case more elegantly, right? And then let's just test it here real quick. Right? It's empty, should be 0. And that should be cool. Uh-oh, that's not good either. Output's 2, but we expect 3. Sort it. What the heck happened? What's going on here? Oh, it's less than or equal. Okay. So the absolute difference. Okay, so it doesn't need to be strictly monotonically increasing. Longest consecutive element sequence. Okay, so that is another corner case, which is somewhat ambiguous, right? So, oops. Let's see. Not strictly increasing is too limiting. Right, we need to relax that constraint. Right, here we go. So basically, relax constraint for strictly increasing values. Right. Okay, so just the absolute difference between these two is less than or equal to 1. Which will allow the input 0, 1, 2, 1 to equal 4 instead of 3. No? Uh-oh. Oh, wait, hold on. It doesn't need, it does need to be in. Oh, wait, okay. So hold on. Oops. Let's see. Submissions. This guy. Outputs 2, expect 3. 1, 2. Oh, okay, never mind. I misread that. So why is this not working then? It should work, right? 1. Oh, okay. We want to remove duplicates then. Okay, fine. All right, let's remove duplicates and then run through it. So let's do this then. Using a set to be ordered set of integers, and we'll just create it. Set epsilon. Set S based on this guy. And then let's do this. For it's equal to step again. Next step again. It does not equal the end of the set. Okay, and then so if we've it's the object and location of the previous iterator plus 1 is equal to the object and location of the current iterator. And best equals the max of best incremental run. Otherwise, run equals 1. Okay, so this is not correct. This is we need to process unique values based on this guy. Okay, so let's stick this in here. Do these other examples into one, that guy. And that should be a good solution, right? That's cool. Need some more coffee. Ooh. Yay, okay. So that's O of n log n runtime, which is the naive solution. Right. So the way to do this in linear time, I'm thinking, is using the union find. So based on union find, we should be able to create the parent representative of a set of adjacent values and then return the maximum cardinality of the connected component. Right, so game plan for O of n, right, linear runtime improvement is to use union find. Okay. Okay, so we need a function to do the find, the parent representative, which will do that recursively. Will capture itself as its own lambda and return piece of x with path compression. Piece of x equals x and x, otherwise find parent union. Okay, so A equals find A, B equals find B. If A is not equal B, then piece of A equals B. There's our parent representatives that are joined together. This is arbitrary choice. Arbitrary choice. Okay, and then we need a set of what's been seen. As an ordered map and a hash table. An ordered map of seen values. So if we have seen the value plus or minus 1, then we will union that. And we still need to remove duplicates as well. Let's see, I think we can modify A using the C++ unique. Yeah, this is what we want. Forward iterator, last iterator. Okay, unique. What's this do here? An iterator of the element follows the last element not removed. What's the result? Results first. Oops. Using default comparison. You resize it based on that end iterator. Not sure if I want to do it this way or not. Oops, I was going to look at that one next. Yeah, let's just use another. I want this to be a set. Yeah, we can just create a set. It's fine, right? So. And don't overthink it. It doesn't have to be perfect. I just create a set. And then we'll just iterate over the set. PIP sub. Let's do this. And you can see the size. And otherwise we'll create the parent representatives of the set. P.n and string at 0 representatives and then disjoint sets. Let's do this actually. That size is not good. Data empty. Otherwise, we want n to be s dot size, the unique values. Each parent representative. And then we'll go through the set one by one and then do the union based on previously seen values. Each value x of the set product y and the vector of x minus 1 and x plus 1. So these are basically adjacent values. So if s dot find y is not equal to s dot n, so it exists in the set, then we'll do the union of actually what the indices. You want to base it upon indices. So let's do this. Let's just create an array that's unique, and it might be easier. Let's do this. All right, there's our set of unique values in linear time, and then we can create a based on s. All right, a. This is a little bit ugly, but whatever. I mean, it doesn't have to be perfect. And I could also spend some time to clean it up later on. And a dot size, and then we'll go through the array. Yeah, that looks cool. Go through the array indices. Is that right? Is this what I want to do? I don't know. I'm second guessing myself. That has to be linear. So need a mapping between the value and its index. Okay. Yeah, whatever, let's just go with it. Create a map, value index. Map m equals, okay, so the value and the index at that value. Okay, so those are the indices. And then we can do one lookups based on that, right? So current index, this value, and index of the adjacent value plus or minus 1 will be unioned together. So the parent representatives are the indices 0 through n minus 1 inclusive. This is getting a little bit ugly, but whatever, I'll just go with it and see what happens. So these are our targets. Target value is, let's do this. Yeah, targets that we're looking for will be a sub I minus 1, a sub I plus 1. If undefined target equals in the end, we'll continue. But we don't have that value, so it's not a possibility to union. Otherwise, if we do have it, then J will equal M sub tar. Wait, hold on. Hold on. Or X and instead this guy, how about this is just what we're looking for. Okay. Then okay, so if we're finding X, which is the adjacent value plus or minus 1, the index of the adjacent value, and then we'll union on J. Okay. And then we'll find the parents and count them. Let's call this guy index, actually. Index, which is a mapping. Index. The index of that value. Index. Index. Jth index of the target value adjacent to the I index. Okay, and then we'll create a map. Word map and for parent counts. Counts. Right, so parent index is find I count sub. Let's do this. Count of the parent representative is incremented by 1. Okay, and then we want to basically return the best count, right? So return best and end. best equals max best and then increment count. Okay, something like that. Cannot capture that guy. That's right. Yeah. Capture it by reference. Okay, so that looks cool. Right, it's verbose, but it seems legit. And that is a linear time algorithm. You can find. And by the way, I've solved this about a year ago. So it'd be cool to compare my solutions from this year to last year. Let's see what I came up with last year. Oh, wow, this is a way better solution. Much more concise. Holy cow. What is this? What did I do? M sub x equals x. Okay, so instead of using the indices, I'm using the values themselves. Okay, that makes way more sense. Use the values, the unique values themselves. T sub x equals 1. What is t? T is the T sub a. Oh, okay, so I'm counting the cardinality of each connected component in T. So when we make B the parent, or when we make A the parent representative of A and B, we add the cardinality of T onto the cardinality of A for the connected component total size. T is an unordered map. Based on the value, which is the cardinality of the connective component. Okay, yeah, so I mean, it's basically kind of the same thing, but I went about it a super verbose way in that I was using indices, which is quite a bit more painful. Now, whatever, we can clean this up real quick. I can refactor this, right? Okay, so instead of using indices, solution above, we can just use the values, like the unique values themselves as the keys for identifying parent representatives of the indisjoint sets. It should be a concise game plan to refactor below. Let's do this, and then I'll stop the recording after this. It's a pretty decent solution. It's good enough. Doesn't need to be perfect. But this is really ugly. It works, but it's kind of ugly. Yeah, so we don't need to set. Yeah, we need the mapping. Okay, so let's get through to this. So if it's empty, then there are no parent representatives as a set. So I might be able to remove that as well. Okay, so map. Let's call it P because it's a good way of denoting parents. And then I like just doing a linear scan for best at the end too. That seems like okay. Let's do that. Let's return the best end. Based on finding parent. So the count. Count is okay, map of count. We can either do this in the union step or we can do it later on. Either way is okay, it's still linear. It's defining of the hx, right? Oops. X of A, find the parent of X, P, or auto X and A, P set X equals X, parent representatives in disjoint sets. Right, we each are a parent of ourselves. It's really ugly. Okay, let's just get rid of that. For each auto X and A, and Y, or Y in X minus 1, X plus 1. If it exists, parent of action, P dot find Y is not equal P dot end, then we can union them, union X, Y. And that looks good. This is our count of parents. Quite a bit more concise this way. Oh, something's wrong. 10, 0, 4, we're counting one too many. Oh, okay, so this is incorrect in that duplicates are not considered properly. Okay, so let's just have union can return the cardinality of the parent, right? Best equals max best. Okay, so it does make sense to do it during the union step. So here we'll update the parent. Return 0. In that case, if we don't actually do anything, there's part of the same connected component. Otherwise, we'll return the count. Let's do this. Count of X equal to 1 initially. Then, so the count, so we're saying B is the parent of A. So the count of B be incremented by the count of A. And we set that, and then we'll return the count of B. Okay, so that should take into account duplicates. Count is initially 1. When you union it, it counts incremented. It sure is taking a while. Okay, it's going slow, but here we go. And this is pretty much like the previous solution I came up with a year ago, I think, right? Oh, it's not right. Expected 1, now it's 0. Okay. Expect 1, but the output's 0. The union, I guess in worst case, you want to return 1. Or actually, it doesn't exist, so best is 1. Yeah, I guess we can return 1 here. That's 0 there, and then we can have that check if A is empty. We can return 0 immediately. Okay, that should take care of it then. Best is always 1 if it's not empty, and it's fine to return 0 if you don't actually union anything. Big money, no whammies. Yay. Okay, so open back up this guy. Compare them. Yeah, so yeah, this is a little bit cleaner, maybe. Whatever. It's kind of interesting though that This one works without that. Oh, okay, I see how that works. Yeah. So we could get rid of that and then not return anything out of union. If I keep track of it in the count for later on. Yeah, so, and this is kind of nitpicking things like refactoring, make it a little bit cleaner. A little bit more concise, but it's kind of the point where it's like, okay, we did like 80% of it, and now we're like fine tuning that 20%. But in the end, this works too. Right, union by index, union by value as well. So, well, whatever, it's good practice just to clean up code a little bit, and we'll return the maximum value of the count. Okay, so if count is empty, return 0, otherwise return the maximum, the object and location of the iterators, maximum element, right? Count begin, count end. The comparison will be based on second, which is the value a dot second x is exceeded by b dot second. And then actually max element, the second of it. Okay, yeah, something like that. To get rid of best and also handle all those corner cases. Oh, that's not cool. Something happened here. Maximum element. Oh, I do want it ascending order, right? Not descending order. I think that looks right. Yeah, okay. I get confused sometimes. That looks good. Okay. So that's basically what I came up with a year ago after I refactored the solution. Instead of using indices, using the values, and then whenever we actually do join the parent of A is B, and like include the cardinality component of A onto B. Right, so there you go. Hey, son. Catch you next time.